Right. I think we can get started. So very happy to have Ramani from Delaware. He did his PhD from Stony Brook, and then the postdocs in Berkeley and then Stanford, and faculty at Delaware. So it's going to talk about improving prospects for detecting Higgsino dark matter.
Yeah, thank you for having me. It's a pleasure to be here. And yeah, I'm going to talk a little bit about a throwback talk in some sense. Like if you just got dropped here, you might think this is the early 2000s in terms of the topic of choice. So I'll try to remind you of things you might have not heard about in the last 25 years as we go. And I just forgot tonight. I have to quit the screen. No, it should work. Yeah. Yeah. I want to point out you could have a very verbose alternate title, and I'm not wedded to Higgsinos, and this is equivalently some new object at the electroweak scale, which is dark matter. I'll talk about how things like this, which you might think are long dead, are not dead. Right. Good. So this is based on a bunch of things. So I've kind of been obsessed over this part of parameter space since my time at Berkeley. So it's a bunch of talks that I want to present. And I'll start with the introduction to the parameter space and summarize kind of what the constraints are, why this parameter space is so difficult to go after. I've probably been looking at WIMPs forever now. And just a summary slide on dark matter. I don't have to introduce this to this audience. There's overwhelming evidence for it. It cannot be explained by the standard model. And it looks like it's critical to things like galaxy formation, to our very existence. So clearly it's a deep and important problem to solve. And you could ask, is it related to problems in particle physics, right? And then in the beginning, we used to do this. And even now, there are a few models that do this. And what I want to point out is that this is one such model where, well, if you take the SUSY version of it, it nicely connects to the electroweak hierarchy. And furthermore, at the weak scale, there's also something else going on that works very well, which is the WIMP miracle. So there's thermal equilibrium and then freeze out. And TV particles, weak scale cross sections naturally produce the correct Relic abundance. And if you take the supersymmetric partners of the standard model, the 1.1 TeV Higgsino and the 3 TeV Reno are natural candidates in that sense. It's just a super predictive theory which solves something else, gives you naturally a dark matter candidate, and also tell you exactly where to look at. Right. So it's slightly different from if you just used to axion parameter space, right? There's just a very unique prediction for where this mass should sit. Right? And once again, if SUSY turns you off, right, and maybe you have reasons for you to be turned off, what I want to point out is that there is a much broader lesson here, which is that we could start taking the W in WIMPs seriously, right, and actually interpret it as having weak scale cross section, actually weak interactions with this time, right? I want to talk about a class of models that are that way. And clearly, this is an important benchmark, right? In some sense, because you might be used to thinking about things like the dark photon, things like that, which interact with the standard model. This is much more minimal in some ways. You're reusing standard model gauge groups, and then you're just putting in a new doublet or a new triplet or something like that, which could be done. And there's some nice papers, if you're interested in things like this, where in some sense they throw the kitchen sink at this problem. They study various different representations of SU2, and then try to understand what the correct mass is, and various different things. I would encourage you to do, right?
The battery is dying. Yeah.
All right. Good. So you could ask in general. Let me constrain myself to the doublet, right? Just because that's just the most common. So let's try to understand what's going on there. And as soon as you say dark matter, you have to ask what is indirect detection, direct detection, and collider prospects for something so simple will be, right? And this is recent work by Ben Safdie, Nikrod, and Linda Zhu, which points out that, for example, something like CTA has very good prospects for looking at I'll just start calling them Higgsinos, okay, because I'm just used to that. Very good prospects for detecting Higgsinos, but it's also pointing out that there is an unknown in this problem, which is the J factor, which is the Milky Way potential. So even if you don't see something, you could always hide behind the unknown here, which is how much dark matter there is in near the galactics. So they're pointing out there are some choices of this unknown profile where you at most reach like 1 sigma. What is this? Yeah, 1 sigma for something like CTA, right? Whereas for most profiles people are used to, they claim pretty reasonable detection possibility or the fact that you could rule it out in the near future with CTA, right? So this is what I want to say about indirect detection. Of course, when you think about weak scale particles, you might think that the LHC is a very good device to look for it, right? It is true for colored particles, but unfortunately, and this is well appreciated, it lags behind when you're looking for electroweak objects. Right? Here's the limit on the Higgsino. Here's the limit on the Higgsino, and it goes to at best like 150, 200 GeV. And then this is, of course, on the charged objects, and then there's a charge neutral splitting here, and then these are the best limits there are for colliders. And then what do we have left? We have left direct detection. And you could ask, okay, this is a simple Z exchange after all. I'm talking about an electroweak doublet. And the cross sections should be 10 to the minus 39 centimeters squared. Right? It's just that cross section. Just put a Z. It's trivial to calculate. This is a tree level diagram, and this should all be ruled out long ago, long ago. We are talking about 10 to the minus 47 centimeters squared type cross sections today, right? And the point is there's an important caveat. And this is not because of some weird perverse model building that just naturally comes out of building stuff, electroweak doublets, right? What's the point? And again, I'll explain this with in the context of Higgsinos. These are Dirac fermions before electroweak symmetry breaking. So this is the mu term. So the mu term is marrying H up tilde and H down tilde. Again, I'm using a 2 Higgs doublet model here. And after electroweak symmetry breaking, diagrams like these, diagrams like this, give a tiny Majorana mass. Give a tiny Majorana mass. And if you're not used to this, this is in some sense the opposite limit of something like seesaw, right? Where you have large Majorana masses and tiny Dirac masses. You're in the opposite limit. And if you again diagonalize the matrix like you would for the seesaw mechanism, instead you would find that these masses which are degenerate just split right after electroweak symmetry breaking. Right? So for this reason, these are called pseudo-Dirac particles. Why? Because they're almost Dirac. If they were right on top of each other, they would just be Dirac particles. But they're really 2 Majorana particles, which are almost on top of, which are just slightly mass bearing. Okay, so that's important thing to know. And the second important thing to know is that you can predict this mass difference, right? At least for the Higgsinos. It is related to, it's just mz squared over m1 or m2, where the mass, this is the mass of the Wino or Bino, right? And of course, and the important point is it's inversely proportional to these masses. Okay? So the larger you put your mass of the Mino or Bino, and typically in these models you want to put them very high, much higher than the Higgsino mass, the smaller and smaller the splitting becomes. Okay, so this is important to remember. So if you push limits on the Wino or Bino to larger and larger masses, say maybe from the EDM or something like that, then you start constraining delta to be smaller than something. So that's how these limits go. And the second important point is that these have only off-diagonal couplings with the Z. Okay, I'll tell you what that means in a second. So we talked about the masses. Now let's get some range for where delta H, this small splitting should lie, right? Again, this is just instructive purposes, okay? This might not mean anything at the end of the day, but you could ask, hey, how heavy can I put my mass of amino or bino? And this is from, I forgot the reference, this is from Rees et al. Matrice, where they're pointing out that if you put the mass too high, there are threshold corrections to the Higgsino. It no longer wants to be at a TeV. Right? So asking for it to be at a TeV restricts how heavy you can put the mass of amino or bino, and that further restricts your delta to be larger than roughly 200 keV or 650 keV. Okay, again, this is just some kind of guideline if you want. Okay, it's not super rigorous, but I just want to point out this number because these kind of numbers will come again, and it's just good to remember these kind of benchmarks when we go about looking at these parameters. Okay.
Ari, can I ask a question? So you've made this point that this can go beyond SUSY, right? So say I'm just trying to add in a new doublet.
Yeah.
So you need this mass splitting. So I guess you can do that by just like having some mixing with some other fermion.
Right.
That
Right.
I get can be pretty generic.
Right.
How generic is it to also get this off diagonal coupling to the Z?
Oh, that's just generic for anything that's pseudo-Dirac. So if you have something Dirac, like forget about even electroweak, right? This is the game you'll play if you had something Dirac and it was charged under dark photons, right? And then you have a tiny Majorana mass, they will become completely off diagonal when they scatter via the dark photon of the standard model.
Oh, okay. All right.
Okay, that's how the mass diagonal eigenstates will look. They'll have they'll have purely off diagonal color.
It doesn't matter how I introduce the Majorana mass.
How you introduce? I mean, there's just one way.
Yeah.
You know?
Okay.
I mean, I have two states.
Yeah.
And I can introduce Dirac and Majorana masses. If you're asking a question, is this just generic more than like a two-component object? I don't know. But in the case of just the vanilla case, this is just complete.
It's a Majorana state. Majorana states can't have charges, so they can't have coupling. Diagonal coupling to the vector current.
Okay. Yeah, I guess that makes sense. Yeah.
Okay. And then so let me just point out that the last missing piece in why direct detection does so poorly, and that comes from let's just try to understand direct detection. Dark matter virial velocity relative to the Earth, you typically use that's roughly 10 to the -3. And in the center of mass frame with nuclei, this has kinetic energy of roughly μv squared, where mu is the reduced matter, right? And dark matter scatters with the standard model target and deposits this kinetic energy, which means that if you have a target, say roughly at the 100 GeV mass, I'm thinking xenon in my head, right? You have 100 keV type energy deposits, right? So you could have a TeV dark matter, you could have 100 TeV dark matter, right? But you're still restricted in how much energy is available for you to play with at around the hundreds of keV scale. Okay, so the dark matter kinetic energy could be arbitrarily larger. It just doesn't matter because of kinematics. Okay. And here comes the point of inelastic dark matter, which is of course pointed out by Neil and David Smith in 2001, and it's more broad than just the electroweak scale or the electroweak sector where I'm applying this to. And the point is this, right? If you have this small splitting between dark matter and this excited state, you will really not see this in the early universe where you're doing all of your thermal processes, where you're setting your relic abundances, right? So you just get that for free. Right, you get that for free. You can retain all the salient features, but then today, if you have a mass deficit, it has to be supplied by the initial kinetic energy, right? Which means that this delta m has to be in the 200 keV thereabout range. If it exceeds it, if it's any higher, then your direct detection experiment will be completely transparent to this kind of dark. If you're not used to seeing something like this, like think. In the standard model, you for some reason decided to not look at Z scattering, right? So the neutrino necessarily has to scatter to an electron via Ws, right? And imagine you put in a neutrino, you have a neutrino beam that's 400 keV, so you cannot make an electron. when the electron has no way to scatter, except in this case, the Z's themselves do something like this. There's purely off diagonal, H0 to H1. Okay, so Neil and David Smith pointed this out, and then there have been subsequent iterations, like Higgsino's have people realized soon after. I'm hoping that's the correct chronology for inelastic dark matter. And then people have looked at dark photons or even dipole dark matter, all kinds of different models, all hinging on this very interesting point that you could have splittings much smaller than the mass scale, and direct detection prospects are completely toast, right? So whereas the typical parameter space shown is cross-section versus mass, there's now a third dimension in some sense. And the third dimension is the splitting, which I'm showing here. And the point is, as I promised, the constraints go away completely. So they start off at 0 splitting at around 10 to the minus 45. This is an outdated plot, right? Now we're going even lower. But then once you hit around 200 keV, there are no limits for Higgsino. There are other experiments which are no longer running now, which use things like tungsten, which can do much larger splittings owing to the fact that tungsten is 180 GeV instead of xenon, which is 110 GeV. So this is the current landscape in some sense, if you want. And the Higgsino is sitting here, 10 to the minus 39 centimeters. And that's the point, right? Because these are electroweak objects, they're super predictive. It's just one line there. And the question is, how much can you reach that line as you traverse up? And the answer is not much. It's around roughly 210 keV thereabouts.
So, all right, let's.
Yeah.
Can I just ask a question? Kind of, sorry for asking about the models. So if I don't want to have all of the complexity of SUSY and I just want the minimal model that has these features,
yeah,
it would be 2 fermionic doublets with a mu term, like psi 1, psi 2.
Right.
And then I want that mu term to be small compared to the.
You want the mu term to be large.
To be larger than the
compared to the electroweak. When after electroweak symmetry breaks, you have the small Myron mass term.
You need like a right-handed neutrino and a UPAL coupling if you want to do it renormalizable. So you need a Weinberg operator. You could just put the Weinberg operator with the Weinberg operator.
I guess this is the Weinberg operator in some sense for. So let me just present one more bit of bad news about Higgsinos. And this is pretty cruel if you peel back to before the Higgs discovery, right? So you could ask, hey, these are tree level diagrams. Why can't I do loop level diagrams, right? I could just complete the loop. So there's H0, H1, sure, but I'll just have one more Z scattering. Apparently, I have ways to give in the cross section in order to discover it. Will that help, right? So it turns out that the answer is a little complicated because there is these very perverse cancellations between different one loop diagrams. Okay? And the one loop diagrams are shown there. And this is an old plot, and you see it's an old plot because the Higgs mass is an unknown in this plot. It's on the x-axis, right? And notice, I mean, how could this possibly be? But you see, this is the doublet cross section. These are the error bars in estimating this cross section. And it has a dip right around 125 GeV where the Higgs was discovered. And the point being, these cross sections are already low, but we're talking about loop cross sections are roughly 10 to the minus 51, 10 to the minus 52 centimeters square for the loop process, which much below the neutrino floor or fog or whatever you want to call it, right? And this last complex WIMPs standing paper generalized this for other representations. And you see that the doublets are sitting here. There's the scalar and the fermion, and you see all of the other representations with slightly better prospects, like something like Darwin 200-ton year can go after most of these different models of wimpy dark matter.
Sorry, where's neutrino floor? It says
Yeah, I guess.
the transparency for projector.
No, I think it's an issue right here. Why am I not seeing it? Sorry, I guess it's slightly below Darwin.
Yeah, so I was wondering how the Darwin 200 compares to the neutrino form.
Good question. I think it's somewhere here. My plot doesn't have it. I don't know.
Maybe it's just faded out because the letters neutrino floor, they're sort of on the diagonal.
It's possible I wrote it and I forgot to draw the line.
Oh.
Could be something as silly as that, but
But it's below Darwin 200. So Darwin 200 would see
yes,
these things.
yes, yeah, exactly. It is often pointed out that EDMs might be our only hope of looking for these particles or setting strong constraints, right? And what is pointed out is that like there are these bar Z diagrams where if there's some order 1 CP violation in the Higgsino sector, it can give rise to electron EDMs, which you will observe. And then things like ACME today or advanced ACME in the future could set constraints on this parameter space. But there's assumptions of tan beta, there's assumptions of order 1 CP violation. And of course, you're allowed to critique all of that and say this is really not a robust limit on this parameter space, but more like, guidelines once again. But if you did take it seriously, right? Collisional Dirac detection, as I'm calling it, to differentiate it from new ideas that I'm going to present in this talk, take you to roughly 0.3 MeV, 300 keV, right? And then there are things from the top, because that's how ACME probes it, right? It's probing this UV scale. And as I told you, the splitting is inversely proportional to the UV scale. So as you keep probing this, the UV scale, you can keep walking down in the splitting, right? And the hope is that we could possibly get these two to meet, but we are far, far away from something like that, right? So advanced ACME has not yet happened. Maybe I shouldn't have shaded it. Even that takes you to roughly 30 MeV. So roughly the 300 keV to 30 MeV window for neutral, for the neutral splitting is the, in some sense, nightmare scenario, or whatever you want to call it, for this Higgsino parameter space. Okay, and the rest of this talk will be about, I think, some very reasonable ideas to cover this parameter space all the way up to almost an MeV. Okay, so you could think of that as a threefold increase or a paltry, very small percent of this in linear space, or a good percent of it in log space.
What is CDD?
So if the Higgsino, so there are Vinos and Vinos, right? Unlike the Higgsinos, the Vinos and Vinos have tree-level Higgs cross-section with a standard model. Right? So if the mass of the Vino keeps increasing, then the mixing between the Vino and the Higgsino reduces, which means that the how do I say this? The inherited tree-level Higgs cross-section decreases as the Vino mass. Does that make sense? And then this delta is inversely proportional to the Vino mass. Hence, you choose delta, you choose what Higgs couplings to this mixed Higgsino states you inherit. As you improve, this is not a new experiment, it's just xenon, except instead of Z exchange, it's Higgs exchange.
Okay, but so direct detection sets both like an IR and a UV constraint on this?
Correct.
Okay.
Correct. So in this case, it's not an off-diagonal coupling, it's an on-diagonal coupling. H0 Higgs instead of H0 H1 Higgs. Because if it were H0 H1, you would again not see it because of kinematics. So the Z is only off-diagonal, whereas the Higgs is diagonal. Yes.
I missed what CDD stands for.
It's a new acronym. DD is direct detection. We're just calling it CDD, collisional direct detection, to differentiate it from other ideas I'm going to present very soon. Okay.
Unfortunately, I have to leave.
Oh, okay.
And other people can explain.
Right. Yeah. So I'm done with setting up this parameter space, which typically takes half the talk. And that's kind of par for the course here. Now I'll tell you about some small ideas in some sense collected from the community, and some even smaller ideas from me, but together can have some large impact on this parameter space. Okay.
Can I add something quick? So
Yeah,
in
please.
that previous plot, that slide before, So here if you demand like unification, does that
Mm.
give any prior on the Higgsino mass scale?
So you're asking some kind of, yeah, I don't know. What
Like,
are the
would
things
it
that
be around 10
contribute?
keV, or if you push it higher, like, does it
Yeah,
mess with it?
that's a good question. I don't know. Yeah. Yeah. All right. So I'm going to discuss some improvements in direct detection. Okay, what are some things you can do? And these are some very I think relatively straightforward to reach things that you can do to modify existing experiments. So let's observe, right? Delta M, what is the bottleneck here? The bottleneck is you have a mu and you have a V, right? And the velocity, the mass is set by either xenon or tungsten, essentially the largest nucleus you can put in your direct detection experiment. And as a community, we've all gotten behind xenon as the answer to this question. Okay. And then second, there is a maximum velocity that's set by the escape velocity of galaxy, right? Escape velocity plus the Earth velocity, a little amount extra over the Earth escape velocity. The point being, if it was any larger, this dark matter would have escaped, right? In a stable galaxy, in a galaxy in steady state, right? The question is, can we do better? So let me attack the V virial. And clearly, maybe I didn't emphasize it enough. All of that observation is for a galaxy in steady state. And there's accumulating evidence that the Milky Way is not in steady state, right? And the standard halo model does not account for things like satellites. For example, it's well known that the LMC around 50 mega year ago made its closest pass yet of the Milky Way at around 50 kiloparsec or so. And this left a high-speed dark matter debris, as well as accelerated. It tugged at the Milky Way dark matter, and it's come under a lot of scrutiny. There are many collaborations trying to look at this phenomenon and try to understand what this Milky Way velocity, what this dark matter velocity will be because of a collision like this. And what this last paper, the Anika Peter and co-paper point out, is that they're doing some hydro simulations of a Milky Way-like galaxy, right? With a LMC-like satellite, and what they are getting, I've adapted a little bit for ease of presentation. Whereas this is the standard halo model, this is the flux as a function of velocity, and you see that it cuts off at around 700 kilometers per second, which is what we are used to. What they are saying is that because of the presence of this event where the LMC passed by, there is a small subcomponent of velocity that goes all the way up to roughly 900 kilometers per second. Okay, it's a small component, all right. But nonetheless, this is something they see in all their they roll the dice many times and they see this velocity subcomponent because of elements.
Are there like error bars?
There are error bars. So I've suppressed them in this. I can show you the paper to show you how. But they're pretty narrow on this on the central what do you call the central line.
The error bars in what sense? In the sense of error bars on what they simulate, because this is a Milky Way-like galaxy.
It's a Milky Way-like galaxy. So
but then there's Milky Way galaxy. So I'm just wondering, like, you could have a relatively narrow uncertainty within the simulation you do, but that doesn't necessarily mean that is what the velocity distribution is in the actual Milky Way.
Right. So how would you know that, right? Unless how would you know that? I don't know if there's. I mean, I don't know if they have the power to just simulate the Milky Way itself. Frankly, I don't know why they stopped short of saying it's a Milky Way-like, presumably because the only things they can match are things like the mass, whereas the entire history of the Milky Way merger might be important.
Well, is this like a stream? This is like a debris stream from the LMC?
It's the entire LMC passing by at around 50 mega
50 megayears.
Well, I'm just wondering, is this because the LMC somehow accelerates something,
Yes.
or is it because the LMC, when it fell in, made some pass and there's some...
It's both. It's both. So there's a little amount of the LNC dark matter just left behind because of tidal disruption, and that component has some of the V infinity of LMC, if you want, like the velocity it had with respect to the Milky Way at infinity before it got accelerated to the escape velocity of the Milky Way. And some of it is the fact that the Milky Way dark matter is no longer in equilibrium, and it's trying to escape the Milky Way potential, but it's not gotten out yet. So this is, in some sense, let's say you had a giga year, then this dark matter would have escaped.
Well, that's, so this is the, so this is the distribution in our frame.
Vicinity, our vicinity.
And so if we're going 230 kilometers per second, this could still be trapped, right? 900 kilometers a second if I had a 650 kilometers a second.
But all of the trapped is by definition restricted within the blue.
Well, but I mean, that blue keeps on going. I'm just saying that what's trapped is V, like what you said before, V escape plus our velocity,
V,
right?
right.
So V escape is 650. I don't know what they use, but if V escape is 650 and we're going 230, then the cutoff would be 880, which is, you know, around where that is. So so this is not, I mean,
I think V escape is usually set at 530.
yeah, I mean,
Right.
there's different, I just don't know what they said, right?
Right. So typical what's assumed here is right. I think in the range of 520, 530 plus 280, which gives you around 730 thereabouts, which is where this blue is stopping. It's precipitous after this. It doesn't ever reach 800 if I'm not.
So this is really every excess. This is all non-equilibrium. Is what you're saying.
All non-equilibrium. In fact, like you take the macro distribution and you abruptly cut it off at the escape velocity, right? That's what I remember you do when you do this. You just put that by hand and deem that any dark matter that's outside is just completely gone. Yeah. So there wouldn't be a single dark matter particle in the standard halo model that's more than say 750 kilometers.
Where's this amazing trippy cartoon is from them?
No, it's from me.
Is this AI generated? Is it Magellan throwing dark matter?
It's Magellan. It's
Magellan.
Ferdinand Magellan throwing dark matter at the end.
I had to try really hard to make ChatGPT do this.
And I forgot that dark matter cannot be black holes.
Well, I mean, it's not. It's. I mean, I had to draw something, right?
Why do you think those are black holes? All right.
There's that gap at low mass, so that's a little bit.
These are Higgsinos, remember? They just like they're not a scale.
All right. So there's clearly some uncertainty in the LMC, right? Because of points you raised, and at least in the paper, I have plots for both the standard halo model with some other things I'm going to point out, and with the presence of the LMC. Okay. So yes, the LMC is going to be a little more uncertain, but you could still, in terms of discovery prospects, ask the question: hey, there seems to be now be a legitimate chance that Higgsino could indeed scatter with the standard model with deltas much larger than what we originally thought was possible. Yes, and so that in terms of limits is what this is showing you, which is that take vanilla direct detection and now put in this extra velocity tail that these people find. What would be the constraints on this parameter space? And you see that just the simple observation takes you to from roughly 250 keV to roughly around 350 keV thereabouts for the Higgsino, right? And again, let's remember that this is the only line in which the Higgsino lives, right? Any parameter down or up is not a Higgsino. It's just there so I can make a 2D plot in some sense. Otherwise, I could just be showing you 1D plots. So that's this. So this just the addition of the LMC adds some parameter space. Of course, it doesn't start at 0. So don't think of this as a doubling in delta just yet. Okay. So some more bad news. Okay. So you might wonder, hey, I'm going all the way to around 800 kilometers per second. And if you do this in your head, 1/2 mu v square for 100 JeV is not 200 keV where it stopped, but 400 keV. Naively, we would have expected xenon to take you all the way to 400 keV. even in the standard halo model, but it stops at 200 keV. Why? Why? Because kinematics for inelastic dark matter is funny. Kinematics asks for the recoil energy to roughly be delta of the splitting, right? That's what's shown here. What is the allowed energy recoil as a function of velocity? Okay, and you see that there are closed contours, which means that a 200 keV splitting would necessarily give at least 20 keV, and its sweet spot is around 120 keV. Right? Whereas typical direct detection experiments work at around 40 keV. How could this possibly be bad news? I'm giving more recoil energy than they need, right? And it is actually bad news. It's very counterintuitive, but there is a lot of background above the 100 keV window for direct detection experiments. So they struggle a bit to extend their analysis to larger energy bins. And it has to do with things like differentiating nuclear and electron recoils and things like that, and the flux they place. And this has been known for a long time, right? So that such a mismatch exists. It was pointed in 2016, and this is the best Panda X could do after knowing this fact. And they extended it from 40 keV to roughly 110 keV in their acceptance to do the best they could possibly do in the traditional way of doing direct detection.
Is this like inherent to direct detection, or is this just because they were focusing on lower recoil length?
So it's a bit of both. So I'm talking to Panda X now to change this, and off the top of their head, they don't know, right? They have not looked at that bin outside at all, right? Mainly because it's pretty contaminated, and the only way for them to get like 0 events or 1 event was to completely cut off, and they didn't lose any signal. But this was Panda X2, where they tried to go as large as possible, but they have more data, and it's not clear if they can have some clever techniques to go about, right? But there's a second question you can ask. Okay, there is going to be a large background, but can I set some limit for my events to not exceed my background, right? This is again something I'm talking to Panda X about to possibly do, to just like, throw caution to wind, open up the parameter space, show this background, but let's see what, maybe it's not 0 events, maybe it's 100 events, but let's see what happens when you open up that parameter space. Right? Okay, so enough bad news, okay? So the rest of the talk is going to be all good news. So the first piece of good news is this, okay? So this should be LH1, I apologize. So suppose somehow you convince the Higgsino, the ground state Higgsino to an excited state Higgsino, right? What happens to it? Again, this is just electroweak, so it's completely predictive. So you could put the charged objects here and the W plus, and the prediction here is that it naturally decays via photon emission. It just has a diagram like this, right? And you can calculate the decay length, again, fully predicted. There is no new parameter in your model. And the decay length for, like, say, 10 to the minus 3 velocity dark matter is around 7 kilometers for 400 keV. Okay, or roughly 1 kilometer for MeV mass distance, right? This I find to be really cool, right, and an opportunity. The point here is the splitting could have been anything, right? Any scale. And it's like this nice sweet spot to do terrestrial detection, right? If it was a micron, it would immediately decay and you would be back to square one. Yes. If it was several parsec, you're like, what are you going to do with the excited neutral Higgsino? But it's just this nice sweet spot that you could do some fun stuff with it, right? For example, I'm looking at this with the Panda X collaboration right now. Okay, typically you do an S1 S2 signal. So you have a Higgsino comes in, it pushes at a xenon, and you have this usual S1 S2 signal that we're all familiar with. But the point is, this excited Higgsino, sure, it'll typically go a kilometer, but 1 every 1,000 times it's going to decay inside a meter. Yeah. It's going to decay 1 every 1,000 times within a meter, or for 400 keV, 1 every 10,000 times it's going to decay within a meter, right? So what we're looking at is the prospects of this what we call S1, S2, S3 signal, where there is a time coincident S1, S2, and so a meter, foot is a nanosecond, right? So we're talking about say a microsecond later, because this travels much slower. You will also see an S3 signal. And the cool aspect is the S1, S2 could happen inside your xenon volume, and S3 could happen in a much larger water vito. Right? Because the energy of the photon is pretty large that they can see it in their water vito. And do time coincidence across. So we are talking to the PandaX collaboration to possibly see does it do better than S1, S2 itself, where like answering your question, where I asked, can you just open it up the parameter space? That is background, whereas this is going to be relatively background. Right. So it's a triple coincidence. It's a pretty dramatic signal to see something like this. Okay. So again, I'm a theorist, so I'm going to make a very optimistic projection, which is that in 10 years and 43 chances is the only optimistic projection I'm going to make. Okay, the rest of them I have background. This I do not have any background information on. Right? And if I make this projection, I do not see a single event. Again, I do not know what it is. It's most probably not going to be this. But if you did, this is the best you could possibly do with PandaX. You could go all the way to roughly 450 keV or so in the splitting for the 1.1 TeV massive field. Okay. Here's the next idea. So why should we restrict ourselves to xenon itself? After all, there's a lot of like lead and uranium on Earth, and this kilometer scale tells us that if it scatters somewhere on the Earth and converts the ground state Higgsino to an excited state Higgsino, it's going to subsequently decay. And you could ask, hey, could that subsequent decay be in your large volume neutrino detector? Right. So this is called luminous dark matter detection, which is a name. It was introduced by Sujit and Peter, I think. And there are subsequent papers by Josh Eby and co, the Fermilab group, which kind of spearheaded this. And they stopped short. They looked at lead, and for reasons I don't completely understand, they did not look at the fact that thorium and uranium are also present in the Earth's crust. Right. So you could include those two. And you could ask, how does this work in a large volume detector, right? So clearly, you want to look at single photon decays, and you want the largest catchment possible. So you want to ask, what is the largest detector that's sensitive to single photons at, say, 200 keV, at 400 keV, at 1 MeV, thereabout? Right? We're looking at a monochromatic photon signal. And the good news is there are these humongous behemoths those are sitting there, which are neutrino detectors, right? Harikrishnan, which we might be familiar with, roughly 4 meters, but something just came online, which is Juno, which is roughly 18 meters radius, right? These are not like figurines; these are actual people working on this Juno sphere, right? And they look so small. And all of this is all covered in low radioactivity scintillator material. And this just came online. So let me start with things which already exist. So Harikrishnan, for example, just purely from the fact that the Harikrishnan is sitting on Earth and there's lead and uranium. So you could just sample how much lead and uranium there are. You see that the limits you can set roughly go to around 400 keV. And this is probably why uranium and thorium were ignored. At least for the Higgsino, they don't have much of an effect, right? So if you reanalyzed Harikrishnan, you could go to roughly 450 keV or so in mass, right? So now comes the next idea, again due to Neil in this parameter space. This paper is called Dark Matter Detection in 2 Easy Steps with Maxim and Itai, where they pointed out that, hey, why should we depend on the Earth? There's, after all, things like lead shielding right outside detectors, right? You could just scatter off of that lead, right? Let's go one step further. And I'm trying to talk to Juno and Cameron to doing something like this. They have several kilotons of pure scintillator material, right? So how difficult is it for them to procure several kilotons of lead? And that's not too expensive. And we don't need Roman lead. We just need to put it around. And most of it is self-shielding. And they have large water vitos and so they're not really perturbed about the natural radioactivity of lead to put somewhere around in the vicinity of Juno or in the vicinity of Cameron. Okay. So this is something I'm talking to them with. And it so happens that at Delaware, one of my colleagues, Spencer Aksani, works in the Cameron collaboration. And I was talking to him about ideas like this. He was telling me that there was such a monochromatic photon search done at Cameron. Okay, so this is the backgrounds they find. So unlike in the S1, S2, S3 case here, I actually have backgrounds to work with. So you could analyze this and set limits or put constraints on this parameter space. So his grad student Masuma is working on this, and if just from the data they have, the green is the kind of constraints they will set. So the reanalysis of data will roughly take you to around 400 K. Okay. But in the future, let's say they put a 5-meter cube of lead or 20-meter cube of lead, they could push this all the way to around 650 to around 450 or 650 K. Okay, kind of splittings. So this is ongoing work. This is already happening. But we also had a nice discussion with Juno, which is again a much bigger detector, which means that you could again do much better with something like lead 20-meter cube. You could go all the way to 700 keV, or with uranium 20-meter cube. So this is just depleted uranium, which countries have a lot of, and there's not much use to it, right? So this is after all the enrichment has happened, and you take all the useful uranium out, you're left with U-238. One of the main uses of this is bullets for anti-tank bullets, because it can penetrate real far, right? It's one of the densest objects now. And there's apparently a more peaceful use of depleted uranium here, which could let you probe all the way up to 800 keV or so, right? So this is all for 1.1 TeV Higgsino. What I'm pointing out here is, let's say you're not wedded to freeze out, right? Let's say there is something else funny happening in cosmology. After all, where did this happen? This happened in the 200 GeV scale, right? Temperatures. And I think we all agree that we don't know much about what happened at 200 GeV. So maybe there was some thermal injection in the standard model, or something else that lets you go to other dark matter masses. Okay. So I'm pointing out freeze out here, and then I'm just pointing out that there is dark matter mass, other dark matter mass, where you retain many of the salient features of dark matter. The only thing you're not retaining in some sense is freeze out. And I'm showing you a plot for the constraints of the dark matter mass versus delta parameter space. So once all of this is done, and at least these parts are definitely going to be done because people are doing analysis, and Juno as well. So we'll go all the way up to 600 keV, starting from the 200 keV, 250 keV we are at pretty robustly, right? I don't see any impediments to something like that. But then going further will involve additions. So you can no longer just piggyback off of existing scientific goals. You need to do things like put a lot of lead in, or this might be a hard sell, like procure the uranium that's just safeguarded by governments to put in very close to your neutrino detectors. But if you do, you can go all the way up to 900 keV in this parameter space. Okay. So that's about what I wanted to say for, in my opinion, very reasonable ways to go about this parameter space. Are there any questions? Then I'll tell you about more unreasonable ways to do this.
So what's this typical time delay for the S3 signal? Like how fast is it traveling?
Right. So let's say xenon is roughly a meter. Dark matter travels at 10 to the minus 3. And I'm gonna it's a foot a nanosecond for light. So we are talking about several microseconds.
This is all assuming the Peter et al. Scalar model, right?
Anika Peter LMC model. But I also have plots, so there are going to be improvements even if you don't assume that.
Right,
They'll
yeah.
just be slightly more modest because you do not have the extra V square.
So in all these like Juno and whatnot, you said you're looking for a monochromatic
Yes.
gamma ray signal.
Yes.
So that's assuming, I guess, that the Higgsino is when it goes to the excited state, it's produced at threshold. If it has some like finite velocity.
Well, okay, here's the deal, right? Remember the Higgsino is a TeV object, and it is moving at 10 to the minus 3, and its momentum transfer is mu times V, which means that the Higgsino really just goes along even after scattering with the nucleus, because the scattered momentum is 0.1 of its momentum.
Okay, so it's still
Yes.
moving at like 10 to
10 to
the
the
minus
minus
3.
3, right?
Does that then give some spread? Oh, I get. Well, I mean, then the spread in there.
There's a Doppler shift, yes.
Yeah, yeah.
But these, you shouldn't think of optics like resolutions here, right? The resolution for Camlan is like 10%.
Okay, all right. So
Right.
it's
I wish you could do something like that, right? Because we could do grade and signal over background, because you can go to tinier and tinier regions, restricted by the fact that at best could do Doppler, but they're nowhere near that. Like Juno in the future hopes to do 3%.
Okay.
Right, but that's futuristic. I don't know if they can reach that yet, and they're nowhere close to that right now. Right, and like the benchmark was set by Higgsino, people are even today finding very difficult to replicate the kind of the low backgrounds and then the energy resolutions that Higgsino did, and people are trying hard to do that, albeit at much larger scale. Okay, good. So I'll rush through something that I've spent a lot of time thinking on. I'm very proud of, which is at the end of the day, right? You're restricted even after all these tricks to roughly 900 kV or so, and it's because you're at the mercy of the energy of dark matter, right? I want to ask the question: is there a concept where instead of energy coming from standard model to dark matter, which is every experiment you could possibly think of, at least in the WIMP parameter space, could you do something opposite, which is where energy goes from dark matter to standard model? Sorry, from standard model to dark matter, right? So something like what I'm showing here, where energy is traveling in this direction, and it just sounds ridiculous just to say it, right? But let me motivate a strategy to do something like that. So let's say there are atoms, atomic states, and this you know from Quantum 101, I'm teaching it right now. There are SPDF levels, right? And these are named, so these are named for angular momentum levels. So S is L equals 0, P L equals 1, and so on, right? Now, if I excite the F level, right, you will typically have a cascade F to D, D to P, P to S, right? What if I engineer for the D and P levels to be removed? What happens? What happens is it is hard to shed J into a single photon, right? Whereas a single photon wants to take away 1 unit of angular momentum. The F to S transition is 3 units of angular momentum. There is a mismatch, right? And as a result, its lifetime quickly balloons up to by alpha to the -2 delta J. The delta J is the angular momentum difference between the excited and ground state. And it makes this excited level metastable. Right? Again, it's called forbidden in quantum mechanics, right? But nothing is truly forbidden. It just happens much smaller. And there's one thing that's truly forbidden. We can talk about that later. Okay. Now, dark matter with orbital momentum J can come in, and it can cause this transition, right? So the idea is, how could we possibly engineer a bunch of metastable levels, say atomic levels, and we trap these levels at the F state? But the F states are happy to live there. We would like for them to live, like, say, a year or so, right? It sounds daunting, But if you could do that, then dark matter with orbital angular momentum to give in this frame could come in, scatter F to S, down scatter, and steal the F to S energy. This is the idea.
Sorry, why alpha to -2 delta J?
Why alpha to the -2 delta J? I'll tell you. So decay works at momentum equals the energy gap of the transition. Yeah. Now, RA is the size of the atom. Yes, and you're probing a Bessel function. This is what transitions you from, say, an S state to a SPDF state, right? So you'll do S of 3 of Q times R. Yes, and for small QR, this is a power law suppression. In fact, it goes as Q to the delta J, right? QR to the delta J. And QR happens to be of order alpha for atoms. And hence, it's alpha to the -2 delta J for the amplitude and square for any kind of rate like the decay, right? If you
if you don't want a mathematical way to answer this, let me answer it in another way, which is you're asking for large orbital momentum, angular momentum to be dumped into a photon, right? And essentially, you want to put the photon out like a frisbee. You want to take it out this way, such that it has orbital angular momentum to you. But it is at radii much larger than where there is wave function support in the atom. Right? That's another way to see the same thing. And they all, at the end of the day, conclude that these decay lengths are times are huge. Whereas scattering does not probe at q equals delta E. Instead, it probes at q equals geometric mean of the reduced mass times delta E. Right? This is typical, right? We know this. We have known this forever. That this is where this is what is probed in scattering. So scattering is at much larger momentum transfers, and hence it looks at the same matrix element, but at much larger momentum transfer where it's not suppressed or relatively less suppressed compared to decay, which means that it prefers to go. But at the end of the day, the point is the same, that scattering has inherent angular momentum to give, whereas decay doesn't. It has to produce its own, so it has to be at much larger R, right? So you could ask, hey, is this some theorist's dream, right? It's just something I made up. But nuclei are sufficiently dirty enough that they can just produce things that you have in your field theory, right? For example, there are things called nuclear isomers, right? These are states with different nuclear spin configurations. So these are not isotopes. They have the same number of protons and neutrons. Correct way to think about them is that they are like the SPDF states of an atom. Yeah, so they arrange themselves in different spin levels, and the spin difference produces this delta E times R nucleus to the -2 delta J. Whereas a typical nuclear transition is a few picoseconds, isomers can have extremely large lifetimes, and they store this energy in this higher excited state, right? And this is crazy, right? I mean, this is nature giving you goosebumps, right? Whereas you should expect a gamma decay to happen in picoseconds. There are isomers which are long enough lived that they can be natural. And the corollary of something like that is that you can just go mine for these isomers and you will just find them. You'll just find these batteries just living inside the earth. Right? And there are some other isomers that are like 2.5-minute isomers, 160-day isomer. And then the king 2.5 MeV splitting is a 31-year isomer that was made in old experiments because there was promise that you could make an isomeric bomb with it. So there was a clamor for making this isomer for producing it in these old nuclear fission facilities. Okay, so I got in with Los Alamos, who had some supply of this hafnium, to see if they can make an isomeric dark matter detector with it. Okay, so this is what I'm showing here. Again, 1 gram of pure hafnium contains a lot of energy, 1.3 gigajoule. But Los Alamos today has roughly a microgram of this hafnium. Far away from what you need, but you can ask what you could do with it. And what we did with it was we asked, okay, what would you do? What could you possibly do? This I like a lot. There are some regular decay channels for hafnium, but then dark matter can make it go through some other states that are not naturally populated in the decay scheme of hafnium, right? Which means that these are much rarer gammas that would otherwise not exist if not for dark matter scattering and pushing it to these states. Okay, so we went looking for these gammas. And we've set an extremely basic limit of 10 to the minus 19, 10 to the minus 20 centimeters square in the mass splitting parameter space. So this was a collaboration with experimentalists at Los Alamos. And you see, it's several orders of magnitude away, right? It's 20 orders of magnitude away. But it's just using some sample that someone threw away in some sense, was just found in a lab. And we're trying to see if we can improve this. Again, this is plagued by the fact that there is just natural background in this parameter space. And the hope is that if you could put something like hafnium inside a box, inside a lead box, and put it next to Juno, and do a light shining through wall type experiments, right? What is showing here is how many kg year you would need to go after the Higgsino at 1.1 TeV. This is a pretty tall task, right? This would involve like, a lot of research into like production mechanisms for the storage. Like it takes an act of Congress to move something like this from one place to another because of the amount of radioactivity involved, right? So the amount of radioactivity involved, previously, the only time where someone even dared to make something like this was the SOX proposal in Russia, where they were going to put this next to Harikrishnan. And it led to some disastrous consequences. So there's lots of doubts about whether something like this will be possible. But this is in some sense my dream, where you could go after like almost 2 to 3 MeV parameter space by building a device that looks like this.
So hafnium, that's the 31-year isotope. So
Isomer.
Isomer.
Yes.
So even with a 31-year decay time per full kilogram, the radioactivity levels would be huge,
right?
So
like
and
I mean, because 10 to the 22 particles per gram, it's 10 to the 25, and then so you see 10 to the 25 particles, one decays every 31 years or so. So it's a lot. Yeah.
And this curve is then assuming 0 background.
No, this curves assume 0 background in Juno. So you can ignore the fact that it's producing a lot of radioactivity, because you say you put it in 3 meters of lead, 4 meters of lead, such that it's many radiation lengths of the natural decay. Instead, the Higgsino picks up this energy, becomes H1, and the H1 subsequently decays inside Juno.
Sorry, what were these the numbers when 78 minutes?
Sorry, what's the question?
In the isomers, you had at least 180.
This?
Minutes. Yes.
Atomic mass.
Oh, so that's the atomic mass,
Right.
which is the same as, because this is
right. They have the same number of protons and neutrons, right? They have a slightly different energy because they're at a different level, but that is minuscule. Like we're talking about an MeV difference in 178 GeV of rest mass. So that number is never written. Instead, this M is written to show that it's an isomer and not the ground state.
Can you do something even more crude of like, just because we've found some of this 180 tantalum that already sets a bound?
You can. That's a bound, but notice how similar to like a proton decay bound, right? The fact that we exist set a limit on the proton's lifetime, but you set a much better limit from actually looking at a proton, a lot of protons for a few seconds.
Yeah.
Right? That's always true. You never beat it's very easy to beat the bound that you ask for, because one, it's the fact that we have lived for 10 to the 10 years, but you can always collect more than 10 to the 10 particles. It's very easy to collect more than 10 to the 10 particles and look at them for a year. Right? So it's always very easy to go one step further than that now. But you're absolutely right, such a bound exists. Yeah. So if you're not wedded to the Higgsino, I mean, this is just motivating more near-term parameter space for this, right? With much less amount of stuff, I can still go after things like freeze out, things like that. It's like 1 milligram here or 10 milligram here amount of radioactive material. So there's a lot of potential. These are also difficult, but they are much easier than producing a kilogram of this radioactive material. So this is kind of the near-term target for this parameter space. I'll skip this and I'll summarize So I'll just summarize. For a few electroweak WIMPs are still left. One example is Higgsino. It's very well motivated, and I think we should all think about this seriously, right? And the issue is that it does not possess enough kinetic energy for traditional direct detection. And what I'm proposing here, if done, like the first part of the talk or most of the talk, with some very straightforward ways to improve, you could hit a 4-fold increase in splitting sensitivity due to the fact that there's an LMC population, and more importantly, by invoking the heavy elements or putting a large sample of heavy elements right next to our detectors. Right? In the future, more wacky ideas like nuclear isomers, things like that, right? And the question is this, right? Why are we working so hard? At least the way I think about it, it might be our only path if these electroweak objects exist to go after them. We might not get another collider in our lifetime. Or Even better, right? You might go after SUSY. This might be our only SUSY signature that's accessible to us in the near future. Right? And in the future, I didn't have time to talk about this. I've thought about various different like hot objects. Forget isomers. Like could we do storage rings, or could you do fusion reactors? They might or might not produce electricity, but they are still very hot. That part is established. Could we use that to possibly springboard dark matter to subsequently detect it? So these are things I'm thinking about. Thank you.
We have had a few questions, but any more questions for Hari? All right, looks like not, but yeah, we can chat more later. But yeah, thanks again for the nice stuff.